Okay, let's dive right in. For today's brief, we are going straight under the hood of AI software agents. We're going to get past all the hype and really understand the nitty-gritty engineering behind how these programs actually think, act, and, get things done. I mean, have you ever really thought about it? You type in a simple request and then, boom, a few moments later, code is getting written, files are updated, complex stuff is just happening. It can feel a little bit like magic, but behind the scenes, there's a really precise, logical process going on. So let's peel back that curtain. So first things first, let's get our terms straight. What we're talking about here is a software agent. And this isn't just the AI model itself, like you might think. It's the whole system, what engineers sometimes call a harness. A better way to think about it is like a conductor of an orchestra, right? It's orchestrating this complex dance between you, the language model, and a whole suite of tools. All right, so at the absolute heart of every single one of these agents is this fundamental process. It's called the agent loop. And it is literally the engine that drives every single calculation, every decision, and every action the AI takes. This loop is kind of like a four-step dance that just repeats. First, you give a command. Pretty simple. Second, the agent takes that, packages it into a really detailed prompt, and sends it to the AI model for inference. That's just the fancy word for the thinking part. Third, the model decides, should I answer directly, or do I need to use a tool, like maybe run a command in the terminal? And fourth, if it used a tool, the output from that tool gets added to the conversation history, and the whole loop starts all over again. This entire cycle, by the way, is called a turn, and a big task might take a whole bunch of turns to finish. Now, let's talk about that second step, sending instructions to the model. This is absolutely critical. It's all about crafting the perfect prompt. But as you're about to see, this prompt is so much more than just a copy and paste of your message. It is a highly structured piece of communication. Before your request is even looked at, the agent has already loaded up the prompt with a ton of context. We're talking about system instructions on how to behave, a complete list of all the tools it's allowed to use, details about your computer's environment, like what folder you're in, and maybe even specific project documents. Your actual message, it's just the final little piece of this really big detailed puzzle. And here's the kicker. That prompt, it's not a one-and-done thing. As this quote explains perfectly, with every single interaction, every tool it uses, every reply it gets, the prompt gets longer and longer. The agent is constantly building out this complete, running history of the entire conversation. Let's actually visualize that. So it all starts out pretty simply, right? You make a request, and this text becomes the very first part of the conversation history that gets sent over to the model. Okay, so the model gets this and thinks, to add a diagram, I probably need to see what's in the file first. So it decides to use a tool, in this case, a shell command, to read the contents of that README file. Now that decision, that function call, gets tacked right onto the history. The prompt just got bigger. So what happens next? The agent runs that command, and it gets the file's content back. And where does that content go? You guessed it, right back into the prompt. So for its very next step, the model is going to be given the entire history, your original request, its own decision to use a tool, and the result of using that tool. It's literally building a running memory of the task as it goes along. Now, this process of remembering literally everything is incredibly powerful, but it also creates two massive engineering challenges: speed and memory. This is where we see performance under pressure. I mean, this is the question that's probably popping into your head right now, isn't it? You're sending more and more data with every single step of that loop. That has to be crazy inefficient. And you would be absolutely correct. It is a huge problem, and it requires some very clever solutions. On top of just the speed issue, there's a hard limit. Every AI model has what's called a context window. It's the maximum number of tokens, think of them as pieces of text, that it can process at one time. Basically, it's the model's short-term memory. If that conversation history gets too long, it literally runs out of room to think. So, to solve the speed problem, engineers use a really cool technique called prompt caching. The idea is, as long as the beginning of the new, longer prompt is an exact match to the one before it, the system can just reuse its old work and only process the new bit at the end. This is super efficient. But, and this is a big but, if anything changes at the beginning, like a new tool is added or you change the folder you're in, it causes what's called a cache miss, and that forces a slow, expensive recalculation of the entire thing. So the key takeaway here is that agents are meticulously designed to keep that history stable to stay fast. Okay, so caching helps with speed, but what about that hard memory limit, the context window? How do you have a conversation that goes on for longer than the model's short-term memory can handle? Well, you engineer a better memory. The solution here is actually pretty genius. It's called conversation compaction. When the conversation history starts getting close to that context window limit, the agent basically asks the model to summarize everything that's happened so far. This creates a brand new, much shorter history that captures the essence of the original, which frees up a ton of space. It's a really clever way to give the agent a kind of long-term memory, letting a conversation go on almost forever without losing the key context. So there you have it. We've seen the core loop, we've seen the careful art of crafting a prompt, and we've seen the clever engineering that's managing speed and memory. By understanding this internal logic, we can start to see these agents not as these magic black boxes, but as complex, rational systems. And that, of course, leaves us with a really fascinating question for the future. As these systems keep getting better and better, just how much of our work are we going to trust them with next?